For 30 years, it has been the battery that was always 5 years away, solid state. The technology that promises to charge an electric car in 10 minutes, give it twice the range of anything on the road today, and never catch fire. The battery that chemists, engineers, and investors have been chasing since the early 1990s, and failing to deliver at scale. In the past 18 months, that changed. Not with a single announcement from a single company, but with a convergence of breakthroughs across multiple labs, multiple countries, and multiple supply chains that has shifted the consensus in the scientific community from eventually to now. The 30-year wait is over. To understand why solid-state batteries matter, it helps to understand what is wrong with the batteries that exist right now. Every lithium-ion battery in every phone, laptop, and electric vehicle on the planet uses a liquid electrolyte to carry charged particles between the positive and negative terminals. That liquid is what makes the battery work. It is also what makes the battery dangerous, degradable, and limited. Liquid electrolytes are flammable. They degrade with every charge cycle. They perform poorly in extreme cold. They require heavy safety systems to prevent thermal runaway, the technical term for the process that causes batteries to catch fire. Solid-state batteries replace the liquid electrolyte with a solid material, typically ceramic, glass, or a polymer compound that carries the same charged particles without any of those drawbacks. No flammable liquid, no degradation, no cold weather performance drop. The safety systems become optional rather than mandatory. The energy density, the amount of power that can be stored in a given volume and weight, increases dramatically. The charging speed increases dramatically. The lifespan extends dramatically. The only problem was making them at scale, at a cost that made economic sense. The manufacturing problem that blocked solid-state batteries for 3 decades was not a chemistry problem. The chemistry was solved on paper in the 1970s. The problem was building the solid electrolyte layer thin enough, uniform enough, and stable enough to function reliably inside a battery cell that gets charged and discharged thousands of times. QuantumScape, backed by Volkswagen and Bill Gates, has been working on a lithium metal anode combined with a ceramic solid electrolyte since 2010. Their cells have now demonstrated more than 1,000 charge cycles at automotive-relevant power levels without significant degradation, a milestone the industry previously believed was years away. Toyota has taken a different path, using a sulfide-based solid electrolyte that can be manufactured using modified versions of existing battery production equipment. The company announced in 2023 that it had solved the key durability problem and is targeting commercial production of solid-state EVs within this decade. Samsung SDI and CATL, the 2 largest battery manufacturers on the planet, have both announced solid-state production timelines. When the companies that make most of the world's batteries say the transition is happening, it is not speculation. It is a supply chain commitment. The practical implications for electric vehicles are difficult to overstate. Current best-in-class EVs, the Tesla Model S long range, the Mercedes EQS, can travel roughly 300 to 400 miles on a single charge under ideal conditions. Real-world range, accounting for weather, speed, and heating or cooling, is often significantly lower, and recharging to 80% takes between 20 and 45 minutes, even on the fastest available infrastructure. A solid-state battery pack of equivalent size and weight delivers roughly double the energy density. That means the same vehicle with the same battery pack volume traveling 600 to 800 miles per charge. It means a compact car with a small battery pack that still exceeds 300 miles of range. The charging speed changes completely. Lithium-ion batteries are limited in how fast they can absorb charge without damaging the liquid electrolyte. Solid-state cells do not have this limitation. The 10-minute charge time that has appeared in presentations and concept cars for years becomes physically achievable rather than aspirational. Electric vehicles are the most visible application, but they are not the most significant one. Aviation has been watching the solid-state battery race more closely than any other industry. Electric flight at meaningful scale requires energy densities that lithium-ion simply cannot provide. Current electric aircraft are limited to short regional routes with small passenger loads, not because the motors or the control systems are inadequate, but because the batteries are too heavy and too limited. A solid-state battery with double the energy density changes the economics of electric aviation completely. Short-haul routes under 500 miles, which represent more than half of all commercial flights globally, become viable candidates for electric propulsion within this decade. Grid storage is the other transformational application. Renewable energy's core problem is intermittency. Solar panels and wind turbines produce power when the sun shines and the wind blows, not necessarily when the power is needed. Storing that energy efficiently and safely at massive scale is the technical challenge that limits how quickly the world can transition away from fossil fuels. Solid-state batteries, at the cost curves their manufacturers are projecting, make grid-scale storage economically competitive with natural gas, peaker plants for the first time. That is not a small thing. That is the missing piece of the clean energy transition. The competition to lead the solid-state transition is now one of the most strategically important industrial races in the world. Japan has invested heavily through Toyota and Panasonic, with government backing and a coordinated national strategy. South Korea has Samsung SDI and LG Energy Solution, both working on competing approaches. China has CATL, which has more battery manufacturing capacity than the rest of the world combined, and has announced a solid-state product roadmap. The United States has QuantumScape solid power backed by Ford and BMW, and a Department of Energy commitment of several $billions to domestic battery manufacturing. The Inflation Reduction Act created financial incentives for domestic battery production that have accelerated investment significantly. The company or country that leads solid-state battery production at scale does not just win the EV market, it wins the energy storage market, the aviation market, and the strategic leverage that comes from controlling the technology that powers the 21st century economy. The internal combustion engine powered the world for 130 years because nothing else could match the energy density of liquid fuel at an affordable price. That constraint is ending. Solid-state batteries are not a better version of the batteries that exist today. They are a fundamentally different technology, arriving at the moment when the infrastructure to deploy it, the charging networks, the EV platforms, the renewable energy grids, is already being built. The 30-year wait produced something worth waiting for. The question now is how fast the rest of the world catches up to what the labs already know.